the night sky has never been truly silent. For billions of years before the first human ever tilted their head back and wondered, the cosmos has been alive with sound, not sound carried through air, but vibrations of energy, signals, pulses, and waves echoing across the void. Radio waves spilled endlessly from pulsars, spinning like cosmic lighthouses. X-rays flared from collapsing stars. The quiet darkness between galaxies was never still at all, but full of faint whispers, if one knew how to listen. For astronomers, this endless stream of cosmic chatter was proof that the universe itself was alive, a breathing organism of unimaginable scale. And yet, there is a thought that unsettles even the most rational mind. What if, overnight, all of it stopped? What if humanity looked to the skies and found only silence? Imagine it. The telescopes trained on distant galaxies begin their work as usual, hungry dishes pointed toward the night. The data streams into the servers, patterns unfolding in waveforms and static. For decades, these patterns have been reliable, bursts, hums, oscillations as steady as a heartbeat. But on this night, the patterns flatten. The graphs fall into still lines. The noise disappears. First, one observatory reports it, then another. Confusion, then disbelief, then fear spreads through the scientific community. It is as though the stars themselves had decided to fall mute, as if the orchestra of the cosmos had ended in a single, terrible pause. And in that pause, a chill spreads across the earth. The unsettling truth is that silence is often more terrifying than sound. The sudden absence implies an event, a break, a force at work. When the forest grows quiet, the predator is near. When the machines of a hospital stop beeping, life itself has slipped away. Silence is not neutral, it is ominous. So when one imagines the universe itself falling silent, the emotional weight becomes overwhelming. What would it mean if the signals that defined our understanding of reality were suddenly gone? Was it a glitch, a temporary blindness in our instruments, or was it something deeper, a change in the very fabric of the cosmos? The silence would not merely be scientific, it would be existential. For generations, humanity has found reassurance in the noise of the universe. We measure our place in time by the light of ancient stars, by the afterglow of the Big Bang, by the rhythm of distant explosions. Every signal tells us we are not alone in the void, that the cosmos is still unfolding, still burning, still alive. If that were stripped away, what would remain? A dark sky, infinite and unyielding, but empty of voice. A stage with no actors, a page with no words. The absence would not just be physical, it would echo inside us as well, stirring questions that most are not ready to ask. At first, scientists might dismiss it. They would speak of interference, of a new kind of atmospheric distortion, of faulty calibration. Teams would run diagnostics through sleepless nights, convinced the silence was nothing but error. But as hours became days, and days became weeks, the explanations would thin. Governments would hold secret briefings, unable to hide their unease. The public would be told nothing, at least not at first. Yet the absence would eventually reach ordinary people, for even amateur astronomers with backyard receivers would notice that the sky had stopped speaking. Rumors would spiral, carrying with them the haunting question, did the universe just die? Such silence would ripple into every field of thought. For the philosopher, it would become a metaphor for human fragility. For the poet, it would be a canvas of despair. For the believer, perhaps it would signal a divine intervention, a final curtain over creation. And for the scientist, it would be both puzzle and nightmare. What kind of force could mute the cosmos? Could it be natural, a sudden collapse of energetic phenomena we thought eternal? Or might it be intentional, an act of intelligence far beyond us, silencing the skies for reasons we cannot yet fathom? The weight of that question is unbearable, yet it draws us in. For silence is not merely absence, it is a message in itself. When the expected sound is missing, the absence becomes the loudest sound of all. Humanity's story has always been written between noise and stillness. We are creatures who cling to voices in the dark, who tell stories around fire to ward off the silence of the night. To extend that instinct to the scale of the universe is only natural. We expect the cosmos to continue its chorus because without it we feel utterly alone. The quiet universe becomes a mirror of our own fears. It asks us to consider whether we have misread the signs, whether we have mistaken temporary patterns for eternal truths. Perhaps the signals we cherish are fleeting, as mortal as stars themselves. Perhaps the silence is not new at all, but always there, waiting, inevitable. And if that is true, then this moment of quiet is not just an interruption, but a prophecy, a glimpse of the end that awaits when entropy finally drains every last whisper from existence. Yet even in this haunting possibility, there is a strange beauty. To imagine the universe falling silent is also to realize how much meaning we have found in its noise. Every pulse, every burst, every faint background hum has been a gift, a clue, a reminder that we are part of something vast. Silence would not erase that history. It would not steal the wonder we have already uncovered. Instead, it would challenge us to decide what silence means. Is it death, or is it transformation? Is it an ending, or the beginning of a new kind of listening? In the end, the night the stars fell silent is less about the cosmos itself and more about us. It is a thought experiment, a mirror, a reminder that the universe does not owe us music. And yet, in our longing to hear it, we reveal something essential about ourselves. We are listeners by nature, waiting in the dark for voices beyond our own. The silence, whether real or imagined, confronts us with the most haunting question of all. What if the universe has spoken everything it had to say, and now it waits for us to answer? The universe has always been imagined as more than empty space. To those who first studied the skies, it was a grand theater of movement and light, but to modern science, it became something deeper, an ocean of signals. With the invention of instruments that could listen beyond the visible spectrum, humanity discovered that the cosmos was alive with echoes. Invisible to the eye but undeniable to our machines, the universe hummed with radio bursts, microwaves, X-rays, and gravitational ripples. It was as though the void itself was filled with breath, each wave an exhalation from a star, a black hole, or the fading memory of the Big Bang. For generations, these signals became more than data. They became reassurance, proof that the universe was not mute but endlessly communicative. And yet, beneath the comfort lies a fragile realization. Every echo we hear is temporary, each sound destined to fade. When the cosmic microwave background was discovered, it was not just static on a screen. It was the ancient voice of the universe itself, stretched thin across time, still whispering to us from nearly 14 billion years ago. To hold that signal was to hold a relic, a direct line to the birth of all things. In it, scientists found patterns that mapped the infancy of existence, the distribution of galaxies, and the seeds of cosmic structure. It was noise, yes, but noise with meaning, a fingerprint of creation itself. If one stood quietly in front of an old television tuned to nothing at all, a small fraction of that static was this primordial echo, touching every home, every eye that ever lingered on the snow of a forgotten channel. It was a reminder that we are forever connected to the origin of everything, that the background noise of the cosmos was always with us. Beyond that ancient whisper came newer voices, fierce and immediate. Pulsars, spinning neutron stars, blinked with precise regularity, sending beams of radio light like cosmic metronomes. These ticking hearts of collapsed suns became our clocks in the universe, so steady that even atomic precision bowed to their rhythm. Quasars, the blazing hearts of young galaxies, roared across billions of light-years, their signals a testament to the raw energy of matter falling into supermassive black holes. Bursts of gamma rays exploded without warning, brief but devastating fireworks that spoke of cataclysms beyond comprehension. Each signal was a story, an unfolding drama playing out across distances so vast that their echoes reached us long after the actors had vanished. The awe of this discovery was always mixed with something darker. For if the universe could speak, it could also fall silent. What made the signals so extraordinary was not their permanence but their fragility. Stars burned out. Pulsars slowed. Quasars dimmed. Even the cosmic microwave background grew fainter as the universe expanded, its frequency stretching until one day it may no longer be detectable at all. The chorus we hear now is temporary, a performance in the middle of time's vast stage. That realization sparked wonder but also unease, for it implied that silence was inevitable. For the scientists who spent their lives listening, the cosmos became less like a cold expanse and more like a living organism. It breathed in cycles, pulsed with rhythms, and erupted in bursts like laughter or grief. The data were not just numbers but a language waiting to be understood. Yet even as we uncovered translation after translation, a question persisted. Was this language meant for us, or were we intruders stumbling upon conversations that would continue whether or not we were here to hear them? Perhaps the signals were not a dialogue at all but an endless monologue of existence, indifferent to listeners. And if that is true, what does it mean when the monologue stops? The mystery deepens when one considers that we have only been listening for the briefest instant. For most of human history, the sky was silent not because it lacked sound, but because we lacked the ears to hear it. In the last century, with dishes stretched across deserts and antennas built in remote valleys, we became aware of the constant chatter. But what if our arrival to this soundscape coincides with its ending? What if, in the immense timeline of the universe, we tuned in just as the orchestra was lowering its instruments, catching only the faintest encore before the hall fell dark? That possibility stirs unease because it reframes everything we know. The hum of the universe has always been a source of hope. If the cosmos speaks, then surely it is alive, vibrant, and full of mysteries yet to be uncovered. The signals have been our proof that something is always happening, that the universe has not gone cold or still. Without them, what are we left with? Silence suggests not activity but absence, not life but its shadow. It suggests that we may be latecomers to a stage already abandoned, the embers of creation cooling as we arrive with our microphones and hope. And yet, there is a strange power in the thought. If the universe's voice is fading, then every moment we capture becomes infinitely precious. Each burst of a pulsar, each flare of X-rays, each faint echo of the microwave background is no longer just data. It is a goodbye, a vanishing signal preserved only because we were listening in time. This realization makes the act of listening sacred, as if our antennas are not machines but memorials keeping alive the voices of a universe that is already slipping into quiet. Still, the imagination resists despair. For silence may not mean death, it may mean transformation. Perhaps what we call quiet is simply a transition to frequencies we cannot yet detect, patterns hidden in layers we have not yet invented the instruments to reveal. What seems like absence could be complexity beyond our grasp, like a symphony too subtle for crude ears. The awe of science lies not in what we know but in what remains unseen. And in the face of potential silence, hope lingers that we have only scratched the surface of a far greater music. The echoes of a living cosmos are reminders of both wonder and fragility. They assure us that the universe has spoken and that we are capable of listening. But they also whisper that voices fade and that even the grandest song has an end. Between awe and fear lies the space where imagination thrives, and it is here that humanity stands, listening to the great choir of the cosmos, uncertain if what we hear are its beginnings, its middle, or its final notes. The forest of stars stretches endlessly, a tapestry of pinpricks of light woven across black velvet. Yet beneath this familiar beauty, the universe hums with a hidden life, invisible to the naked eye but unmistakable to those who know how to listen. Every galaxy, every collapsing star, every cosmic event sends forth waves that ripple through space, carrying energy, information, and history across billions of light years. To the untrained observer, the sky is serene and unchanging, but to the instruments designed to capture the faintest whispers of the cosmos, it is alive with constant chatter, a symphony of the unimaginable playing in frequencies humans are only beginning to understand. The sound of the universe is everywhere, even when it seems there is only silence. Long before we could tune into these cosmic signals, humanity imagined the heavens as alive. Ancient civilizations charted the stars, read their patterns, and believed the cosmos communicated in subtle signs. Today, we measure those same skies with radio dishes, X-ray telescopes, and gravitational wave detectors, transforming myth into precise science. Pulsars spin like lighthouses, their beams of radiation ticking with absolute regularity. Quasars blaze from galactic cores, sending furious bursts of energy that outshine entire galaxies. The faint afterglow of the Big Bang, the cosmic microwave background, still whispers across the universe, a message from creation itself. All these signals converge to paint a picture of a universe that is far from quiet, that is vibrant, dynamic, and alive in ways we are only beginning to comprehend. Yet there is a fragility to this cosmic orchestra. Stars die. Black holes consume everything nearby. The expansion of space stretches signals until they may become undetectable. Every whisper we hear is fleeting, a temporary message in a vast, indifferent cosmos. The knowledge that this noise is ephemeral adds a layer of tension and urgency. It is a reminder that the universe, despite its apparent permanence, changes and evolves, and that silence could arrive without warning. The notion of a suddenly quiet universe is both terrifying and irresistible, a mystery that beckons us to understand what it would mean if the cosmic symphony abruptly ceased. For the scientists who have dedicated their lives to listening, the universe is not a cold, empty void but a living organism. Its signals are the pulse and breath of cosmic life, revealing structures, events, and processes invisible to the human eye. Each signal carries meaning. A pulsar's precise beat acts as a celestial metronome, a supernova's outburst tells of creation and destruction, a quasar's flare displays the raw power of matter spiraling into a black hole. This ongoing dialogue, conducted in the language of energy and waveforms, has always reassured humanity that the universe is active and intelligible, even if only partially so. The fragility of these signals becomes more pronounced when imagining what would happen if they stopped. A sudden absence of cosmic noise would reverberate through every layer of scientific understanding. Observatories would scramble to check equipment, satellites would transmit empty data streams, and theories would be questioned. Beyond the immediate scientific disruption lies a deeper existential dread. If the universe could go quiet, what does that imply about our place within it? The silence would be an absence that resonates as profoundly as any sound, raising questions that reach far beyond physics or astronomy. It challenges the human assumption that the universe is a stage continuously active, prompting reflections on isolation, impermanence, and the limits of knowledge. Even as silence threatens to unsettle, it also sharpens awareness of what we have discovered. Each detected pulse, each measured wave becomes a treasure, a fragment of the universe preserved in memory and record. The act of listening transforms into an act of stewardship, a way of honoring the fleeting nature of cosmic information. It reminds humanity that we are both observers and participants in a larger unfolding narrative, where the absence of signal may itself carry profound meaning. Amid these reflections, hope persists. Silence does not necessarily mean cessation. It could signify frequencies yet undetectable, phenomena beyond our instruments, or patterns hidden in complexity we are only beginning to unravel. The universe's quiet moments may mask a more intricate symphony, one that requires patience, ingenuity, and expanded perception to decode. The tension between silence and discovery becomes a driving force, a reason to keep building, observing, and listening. Each faint signal recovered from the dark is both reassurance and challenge, a promise that the cosmos still holds secrets waiting for humanity to uncover. Thus, the echoes of a living cosmos are both awe-inspiring and fragile. They encourage wonder, provoke fear, and invite contemplation. Every signal, no matter how faint, is a reminder of the universe's vastness and vitality, while the possibility of silence compels reflection on impermanence and our place within the cosmic order. Between presence and absence, sound and silence, humanity stands as witness and interpreter, poised to understand what it means to exist in a universe that speaks, and may one day fall quiet. The first time humanity truly began to listen to the cosmos, it was like stepping into a hidden cathedral, vast and silent, yet vibrating with secrets. Early astronomers relied on their eyes alone, charting the stars and noting their movements, imagining the heavens as a canvas of divine patterns. But vision could only reveal so much. There were murmurs, signals, whispers beyond the visible, waiting to be heard. It was not until the invention of radio astronomy that humanity discovered the universe was alive with communication of a type we had never before imagined. Large parabolic dishes, gleaming in the sunlight or frozen in remote deserts, became our ears to the sky, capturing vibrations that had traveled billions of years to reach us. Each wave recorded was a message, a pulse, a story encoded in energy. In those early days, the first detections were subtle, almost imperceptible, faint bursts, strange patterns, enigmatic signals that hinted at a complexity beyond comprehension. The 1930s and 1940s marked the beginning of this revolution. Carl Jansky, a radio engineer, first detected a persistent hiss coming from the Milky Way, a discovery that revealed that the sky itself was speaking in a language we had yet to understand. Soon after, Grote Reber built the first dedicated radio telescope, scanning the skies from his backyard observatory. What he uncovered was astonishing. The universe emitted signals across the spectrum, from steady hums to sudden bursts, each carrying information about distant stars, galaxies, and cosmic events. The cosmos was no longer a silent stage. It was a living network of phenomena, speaking in tones and pulses that instruments could translate into data and eventually into knowledge. This newfound ability to listen sparked dreams of contact beyond Earth. The notion that other civilizations might also be transmitting signals across the stars became a tantalizing possibility. Project Ozma, initiated in the 1960s, was humanity's first serious attempt to detect such extraterrestrial communication. Antennas were trained on nearby stars, patiently scanning for patterns that could not be explained by natural sources. Even in the absence of a confirmed detection, the act of listening transformed human imagination. The universe was no longer an empty void. It became a stage for potential dialogue, a network of communication that might extend far beyond our planet. The early listening devices revealed more than just hope. They revealed the unexpected. Pulsars, discovered in 1967, blinked in precise, rhythmic intervals, initially puzzling astronomers with their regular signals so perfect they were jokingly referred to as LGM, or little green men. These were not signs of extraterrestrial intelligence, but the discovery exemplified the astonishing complexity of the cosmos. The universe had a language of its own, intricate and precise, yet entirely natural, waiting for human ingenuity to decode it. Each discovery pushed the boundaries of understanding, showing that listening is not merely passive. It is an act of exploration, of interpretation, of expanding perception beyond our immediate senses. As radio astronomy developed, the scale of listening grew. Arrays of telescopes, sometimes spanning continents, began to synchronize their observations, combining signals to create a clearer picture of distant phenomena. From these data, humanity learned to detect the invisible, the faint afterglow of the Big Bang, the whirling jets of quasars, the subtle distortions caused by gravitational waves. Listening became not just an endeavor of curiosity but a tool to map the very structure and evolution of the universe. The act of paying attention, of turning our instruments skyward and holding still, revealed the hidden architecture of reality. Every burst, every pulse, every fluctuation became a message from a cosmos that had always spoken but was only now being heard. Yet there is a haunting quality to this first listening. The more we tuned in, the more we realized that silence was possible. Instruments can fail. Signals can fade. Stars can die. Each discovery carries the implicit knowledge that the universe is impermanent, that the conversation might end as suddenly as it began. The story of these first listening devices is a story of both triumph and tension. Triumph in the unveiling of cosmic voices, tension in the awareness that one day, perhaps, the voice might vanish. The instruments themselves, once marvels of innovation, are fragile reminders that the act of listening requires maintenance, vigilance, and patience. Beyond the technology lies the imagination it inspires. To listen is to hope, to anticipate, to wonder about the unknown. The first devices were not just machines, they were extensions of human curiosity, a manifestation of our desire to connect with something far greater than ourselves. Every faint signal recorded in the silence of a desert or atop a mountain tells a story of human daring, of the audacity to reach out into the vast emptiness, and of the humility to realize how small we are in comparison to the cosmos. And so, the first listening devices mark a pivotal moment in human history. They transformed our relationship with the universe from passive observation to active engagement. They revealed that the cosmos is alive with signals, a network of rhythms and pulses spanning unimaginable distances. They remind us that the act of listening is as much a philosophical and emotional endeavor as it is a scientific one, a testament to humanity's enduring desire to understand, to connect, and to find our place in the eternal chorus of the stars. The universe is a vast symphony, and over the decades humanity has learned not only to listen but to understand some of its most intricate melodies. What began as faint static on an early radio telescope has grown into a comprehensive map of cosmic signals spanning the electromagnetic spectrum. From radio waves to X-rays, from gamma rays to gravitational ripples, each form of energy reveals a hidden facet of reality. The universe speaks in patterns, and scientists have become translators, deciphering the signals to uncover secrets that would otherwise remain invisible. Every discovery, every new detection has transformed noise into knowledge, turning abstract vibrations into concrete understanding of the cosmos and our place within it. Consider pulsars, the remnants of dead stars spinning with astonishing precision. Their beams of radio waves sweep across space like cosmic lighthouses, ticking with a rhythm that rivals the most precise human-made clocks. By tracking these pulses, astronomers can measure distances, probe the interstellar medium, and even detect the subtle warping of spacetime itself. What once seemed like random bursts are now understood as celestial signatures, providing insight into the physics of extreme environments. In each pulse, the universe communicates its inner workings, revealing the power and complexity of processes billions of years in the making. Then there are quasars, luminous beacons at the hearts of young galaxies whose energy output can outshine entire star systems. The violent accretion of matter into supermassive black holes creates jets and flares that travel across unimaginable distances, carrying information about the dynamics of galaxies, the behavior of matter under extreme gravity, and the early evolution of the universe. By interpreting these signals, scientists can reconstruct events that occurred billions of years ago, effectively looking back in time. Noise becomes narrative, energy becomes evidence. The universe is not silent. It is a storyteller, chronicling its own history in bursts and hums that until recently we were incapable of reading. Gravitational waves added a new dimension to this cosmic conversation. Detected for the first time in 2015, they are ripples in spacetime itself, generated by cataclysmic events such as colliding black holes or neutron stars. Unlike electromagnetic waves, which can be absorbed or scattered, gravitational waves carry pristine information across the cosmos. Their detection transformed our understanding of the universe, offering a way to hear events that would otherwise be invisible. The universe, in its own voice, reveals violence and majesty, destruction and creation, all encoded in subtle distortions of the very fabric of reality. Each of these discoveries has heightened both awe and unease. The cosmos is alive with signals, but none are eternal. Stars burn out, black holes consume their surroundings, and the expansion of space stretches signals thinner with each passing moment. What seems constant is in reality fleeting. This duality, immense permanence paired with fragile temporality, creates tension. Humanity stands as a witness to a performance that has been ongoing for eons, yet each signal carries the implicit warning that the music will not last forever. Knowledge, like the signals themselves, is provisional, and the universe, no matter how much we learn, may one day fall silent. The process of transforming noise into knowledge is painstaking. Massive datasets, once mere static, are parsed for patterns that indicate phenomena such as exoplanets transiting distant stars, black holes consuming matter, or the subtle gravitational dance of galaxy clusters. Artificial intelligence now assists in decoding the sheer volume of information, revealing anomalies that might otherwise be missed. Each interpretation brings us closer to understanding cosmic processes, yet each also underscores how much remains unknown. The universe's language is complex and multilayered, and humanity has only learned the alphabet. This accumulation of understanding has philosophical implications as well. By interpreting cosmic signals, we gain perspective on our own existence. The universe, through its bursts and pulses, teaches patience, humility, and curiosity. We are participants in a larger narrative, observers translating the whispers of creation into comprehension. The noise of the cosmos reminds us that life is fleeting, that patterns emerge and fade, and that silence is not merely absence but a potential state of being. The act of listening becomes a bridge between knowledge and existential reflection, between scientific pursuit and human meaning. Ultimately, transforming cosmic noise into knowledge is a testament to the human spirit. It illustrates our capacity to perceive beyond immediate senses, to construct instruments that extend our perception, and to decode signals that have traveled billions of years to reach us. Each discovery reinforces that the universe is intelligible, that patterns exist, and that our curiosity is justified. At the same time, it reminds us that the cosmos operates on scales of space and time far beyond our comprehension, and that every piece of knowledge carries with it the shadow of impermanence. In learning to read the universe, we learn about ourselves, our ingenuity, our longing, and our place in a story far greater than any individual life. The universe has always been more than a collection of stars and galaxies. It is a puzzle, a mystery that defies simple explanation. Over the centuries, scientists and philosophers alike have speculated on why the cosmos behaves as it does and, more recently, why it might suddenly go silent. Several theories have emerged, each offering a different lens through which to interpret the potential disappearance of cosmic signals. Some are rooted in physics and cosmology, some in the behavior of civilizations, and some in the unsettling possibility that silence might be intentional. Together, these hypotheses form a tapestry of ideas, each more thought-provoking than the last, challenging humanity to confront both the scale of the universe and our own limitations in understanding it. One leading scientific possibility is natural evolution on a cosmic scale. Stars are born, live, and die, sometimes exploding as supernovae, sometimes collapsing quietly into black holes. Entire galaxies can fade as star formation slows and matter is consumed or dispersed. Over billions of years, such processes could lead to stretches of space devoid of detectable signals, creating pockets of silence that expand as the universe ages. Entropy, the inevitable increase of disorder in all systems, acts as a cosmic clock, slowly draining energy and reducing the intensity of emissions. In this sense, silence is not a disruption but a natural consequence of the universe's life cycle, a reminder that all things, even celestial, are transient. Another intriguing possibility is linked to the idea of civilizations and the so-called Great Filter. This theory suggests that intelligent life, if it exists elsewhere, may inevitably self-destruct before it can communicate across interstellar distances. Perhaps the universe has never been as noisy as we imagine. Perhaps the signals we hear are exceptions, rare flashes from civilizations that briefly survived long enough to make themselves known. If true, the silence is not accidental but indicative of a profound, unsettling truth. Intelligent life is ephemeral, and the cosmos may always be largely empty of conscious listeners. The absence of signals becomes a mirror, reflecting not just the nature of the universe but the potential fragility of our own species. Some theories are more radical, proposing that silence could be intentional. Perhaps advanced civilizations, aware of the dangers of broadcasting their presence, actively suppress signals to avoid attracting predators or competitors. In this scenario, quiet is not passive. It is deliberate, a form of cosmic strategy. The idea is unsettling because it implies that the universe is not merely indifferent to us but may contain forces or intelligences actively shaping what we can perceive. The implications are staggering. Every radio telescope, every listening device becomes not just an instrument of discovery but a probe into a landscape potentially governed by unknown intelligence. There are also philosophical considerations. Some thinkers suggest that silence itself is a form of communication, a statement embedded in absence. The universe may not speak in ways humans recognize, and what we interpret as emptiness could be a language we are not yet equipped to decode. This perspective reframes the problem entirely. Rather than seeking lost signals, humanity might need to develop new ways of listening, new frameworks for understanding patterns, and new definitions of presence and absence. Silence in this sense is not a threat but an invitation, a challenge to expand the boundaries of perception and cognition. Astrophysicists, cosmologists, and philosophers alike grapple with these theories, aware that each carries both awe and dread. The idea that the universe could cease to broadcast its signals forces a confrontation with mortality on a cosmic scale. It challenges assumptions of permanence, stability, and accessibility of knowledge. The cosmos, in all its grandeur, may be indifferent or even hostile to human expectations, and the sudden absence of signal would be a profound reminder of that reality. Yet the very existence of multiple plausible explanations offers hope and curiosity. Natural evolution suggests processes that can be studied and understood. The Great Filter frames our survival as a challenge, urging innovation and caution. The possibility of deliberate silence hints at intelligence and complexity, even if hidden. Each theory, whether comforting or terrifying, serves to stimulate exploration, debate, and wonder. Humanity is compelled to continue listening, refining instruments, expanding reach, and probing deeper into the mystery of existence. In the end, the great cosmic silence theories embody both fear and fascination. They highlight the fragility of perception, the limits of knowledge, and the infinite possibilities that lie beyond our current understanding. Whether the quietude is natural, intentional, or simply a reflection of our inability to comprehend, it forces reflection on what it means to exist in a universe that is vast, dynamic, and full of secrets. Each unanswered question becomes a hook, drawing scientists, philosophers, and dreamers alike toward discovery, toward vigilance, and toward the profound acknowledgement that the universe, for all its apparent generosity, may still hold mysteries we are not ready to hear. Stars burn with brilliance, their light and energy illuminating the darkness, yet all stars are mortal. They are born from clouds of gas and dust, live for millions or billions of years, and eventually exhaust their fuel, fading into white dwarfs, neutron stars, or black holes. This inevitable decline is part of a process astronomers call entropy, a measure of disorder that governs the evolution of all matter and energy. On cosmic timescales, the universe is gradually winding down. Galaxies drift apart, star formation slows, and energy spreads thinly across an ever-expanding space. To imagine this is to confront a profound tension. The same universe that dazzles with creation is also inexorably marching towards silence, a heat death in which no energy gradients remain and all activity ceases. Entropy is not a sudden event, it is the slow fading of the cosmos. Light from distant galaxies stretches into oblivion as space itself expands. The cosmic microwave background, the afterglow of the Big Bang, grows ever fainter, its whisper cooling into near undetectable levels. Stars flicker and die, and black holes, insatiable and eternal, consume matter that might have fueled new life. In this vision, the night sky, now bright with celestial fireworks, gradually darkens into a muted expanse. The universe becomes still, not with violence but with inevitability, and silence is the natural consequence of entropy's unrelenting progress. Yet even in this bleak picture, there is cinematic grandeur. Imagine standing on a distant planet, looking up as galaxies drift apart like islands in a cosmic ocean. The light from billions of stars is stretched, reddened, and ultimately extinguished, leaving the sky a dark, featureless void. Neutron stars continue to pulse, but their numbers dwindle. Quasars, once brilliant as cities, collapse into darkness. The universe becomes a ghostly echo of its former self, vast and infinite yet quiet. The scale is so immense that human perception can barely comprehend it, and yet every photon lost, every signal fading, is a note in the gradual symphony of cosmic silence. Entropy also challenges our understanding of time and causality. Events that seem distant or abstract unfold over scales that dwarf human experience. Civilization, planets, and even stars are brief flickers in the lifespan of galaxies. The fading of cosmic signals is not abrupt but a creeping inevitability, a reminder that the universe is dynamic yet ultimately temporary in its activity. To contemplate this is to confront both awe and fear. Awe at the scale and majesty of cosmic processes, fear at the impermanence that defines existence itself. Black holes, in particular, play a haunting role in this process. These singularities of gravity consume matter, light, and energy, creating regions of the universe from which nothing can escape. Over trillions of years, as more stars succumb to gravity, the observable universe will contain fewer sources of light and signal. Even the remnants of once vibrant galaxies will slowly dissolve, leaving a quiet expanse where the echoes of creation can no longer reach observers. In this cinematic vision, black holes are both destroyers and keepers of secrets, shaping the final silence that entropy brings. Yet within the concept of heat death, there is a strange beauty. It is a universe that has fulfilled its cycles, a cosmos that has played its symphony in full, from the birth of stars to the collapse of galaxies. Every pulse, flare, and signal that has traveled across space is a record of existence, a narrative of creation and destruction. In imagining entropy, we are reminded that life and motion are precious not despite their impermanence but because of it. The silence that follows is not cruel. It is the natural endpoint of a process that has been unfolding since time itself began. For humanity, the implications are both scientific and existential. Scientists can model the fading of light, predict the cooling of stars, and explore the distant future through mathematics and observation. Philosophers and dreamers confront the emotional weight. If the universe is destined for silence, what does that mean for meaning, purpose, and observation? Our current era, filled with vibrant signals and celestial noise, becomes a fleeting window, a precious moment in the lifespan of the cosmos when activity, life, and communication are possible. Ultimately, contemplating entropy and heat-death forces a dual awareness of the vastness and dynamism of the universe and of its inevitable march toward stillness. It is a lesson in humility and awe. The universe that once seemed eternal in its light and sound is, like everything within it, subject to decay and cessation. The fading of cosmic signals is both an endpoint and a mirror, reflecting the transient beauty of all existence. Even as we listen to the hum of pulsars or the afterglow of the Big Bang, we are hearing the final verses of a long song, a prelude to the quiet that will one day dominate the cosmos. The night sky is rarely as empty as it appears. Beyond the visible stars lies a hidden web of signals, vibrations, and pulses, some from objects so distant that their light has traveled billions of years to reach us. Among these are fast radio bursts, or FRBs, one of the most enigmatic phenomena discovered in recent decades. First detected in the early 2000s, FRBs are intense flashes of radio waves lasting mere milliseconds yet releasing as much energy in an instant as the sun emits in days or even months. Their origins remain largely unknown, and their unpredictability only deepens the mystery. Every detection raises urgent questions. What produces these bursts, and why are they so fleeting? Are they natural, perhaps from magnetars or colliding neutron stars, or could some be artificial, signaling an intelligence far beyond our own? The very existence of FRBs underscores the universe's tendency toward both wonder and unease. The peculiar nature of FRBs makes them perfect examples of the tension between signal and silence. Most of the cosmos is quiet, or so it seems, but FRBs punctuate that quiet with sudden, explosive events. They challenge astronomers to listen constantly, for any lapse could mean missing an entire event. Even when captured, these bursts reveal only fragments of their story. Their brevity is matched by their intensity, a cosmic Morse code that teases with incomplete messages. Scientists analyze dispersion measures, polarization, and frequency drifts to understand their source, yet no single explanation fits all observed bursts. It is as if the universe itself enjoys playing a game of hide and seek, offering glimpses of understanding while maintaining ultimate secrecy. The mystery of FRBs also illuminates our relationship with time. Because these signals travel vast distances, they reach us delayed by millions or billions of years. Some bursts originate from galaxies so distant that their light left before Earth itself existed. In listening to them, we are eavesdropping on the ancient past, hearing echoes of events long gone. There is a cinematic, almost haunting quality to this realization. A signal arrives bright and instantaneous, carrying the story of an event that may no longer exist. The universe speaks across time, and we are privileged yet humbled listeners. Scientists are racing to capture and interpret these elusive phenomena. Radio telescopes equipped with wide-field surveys constantly scan the sky, while machine learning algorithms sift through mountains of data to detect the briefest flashes. New facilities like the Canadian Hydrogen Intensity Mapping Experiment and the CHIME telescope have revolutionized FRB detection, revealing patterns previously invisible. Some bursts repeat, others are one-offs, and the discovery of periodic FRBs has only intensified the debate over their origins. Each new detection is a thrill, a glimpse of the unknown, and a reminder that the universe still holds secrets beyond our comprehension. The potential origins of FRBs are as varied as they are astonishing. Some scientists propose they arise from magnetars, neutron stars with immensely strong magnetic fields, releasing energy through starquakes or magnetic reconnections. Others speculate more exotic sources, colliding black holes, interactions between neutron stars, or even phenomena as yet unimagined. A small fraction of researchers cautiously entertain the idea of artificial origins, suggesting that some bursts could be engineered signals, perhaps sent by advanced extraterrestrial civilizations. While no evidence yet supports this theory, its very consideration highlights the openness of science to possibilities that challenge preconceptions. The discovery of FRBs emphasizes both the power and the fragility of listening. The bursts are fleeting, unpredictable, and rare, yet they carry profound implications. They force humanity to remain vigilant, to innovate technologically, and to think creatively about the cosmos. At the same time, their suddenness reminds us that silence dominates the universe. For every FRB, countless other events occur unnoticed, lost to distance, faintness, or brevity. The universe offers only glimpses of its workings, leaving the rest shrouded in quiet mystery. There is also a philosophical weight to the study of FRBs. These brief, energetic events are reminders of the limits of human perception, the scale of cosmic processes, and the fleeting nature of signals across vast distances. They provoke wonder, fear, and curiosity simultaneously, compelling us to confront questions about causality, existence, and the possibility of intelligence beyond our understanding. Listening to them is an exercise in patience, humility, and imagination, a bridge between empirical science and existential reflection. In the grand narrative of cosmic noise, FRBs are punctuation marks, startling and dramatic, forcing us to re-evaluate assumptions about order, randomness, and purpose. They illustrate that the universe is not uniformly silent or static but capable of sudden revelation, bursts of energy that disrupt expectations and challenge comprehension. They also remind us that even in the apparent stillness of space, life and activity continue on scales both immense and intimate, often beyond our immediate perception. Ultimately, fast radio bursts exemplify the interplay between silence and sound, mystery and discovery. They are fleeting, energetic whispers in the cosmic void, inviting exploration while preserving enigma. They compel humanity to listen harder, think deeper, and accept that some answers may forever lie just beyond reach. In every FRB, we glimpse the duality of the universe. It is both knowable and unknowable, predictable and capricious, filled with signals yet dominated by silence. Galaxies are not solitary islands in space. They exist within vast cosmic networks, weaving a complex tapestry of matter, energy, and motion. These structures, from spiraling arms to dense elliptical cores, are the arenas where stars are born, live, and die, creating a continuous flow of light and signal across the universe. Each galaxy is a microcosm filled with trillions of stars, nebulae, black holes, and unseen dark matter, all interacting in patterns that generate detectable phenomena. The collective behavior of galaxies produces a symphony of cosmic noise, electromagnetic waves, gravitational interactions, and high-energy emissions that fill space with messages waiting to be decoded. Observing galaxies is like listening to a choir composed of countless individual voices, each contributing to a vast, intricate composition. The study of galaxy clusters reveals another layer of cosmic communication. These massive assemblies, containing hundreds or thousands of galaxies, exert gravitational forces that warp spacetime, creating ripples detectable as subtle distortions in light. As galaxies collide and merge, bursts of star formation light up their cores, while supermassive black holes at their centers release energetic jets visible across billions of light years. These interactions generate a complex network of signals, from X-rays to radio waves, that map the dynamics of matter on scales unimaginable to human perception. In a sense, the universe uses galaxies as both instruments and messengers, conveying information about mass distribution, cosmic evolution, and the hidden structures of space. Yet even galaxies are subject to impermanence. Stars exhaust their fuel, galactic cores fade, and interactions slowly redistribute matter across the cosmic web. The radiation and signals we detect are snapshots of transient events, each telling a story of activity long past. Because light and energy take millions or billions of years to reach Earth, we are always observing history, not present reality. A galaxy glowing brilliantly in our night sky today may already have transformed or even ceased to exist by the time its light reaches us. The signals we rely upon are echoes of a universe in flux, emphasizing both the fragility and the richness of cosmic communication. Dark matter adds another dimension to this invisible dialogue. Though it cannot be seen directly, its gravitational influence shapes the formation and evolution of galaxies. By mapping distortions in light caused by dark matter, astronomers uncover the hidden scaffolding of the universe, revealing pathways along which matter flows and galaxies coalesce. In this way, the silence of dark matter is paradoxically loud. It communicates through its effects, whispering secrets about the universe's structure, its hidden mass, and the forces governing cosmic evolution. Understanding these invisible signals requires not only sophisticated instruments but also imaginative interpretation, as we translate absence into knowledge. Supermassive black holes residing in the centers of most galaxies act as both destroyers and broadcasters. Their immense gravitational pull consumes surrounding matter, creating accretion disks that emit powerful radiation. Occasionally, these black holes launch jets that extend thousands of light years, sending radio waves and X-rays across intergalactic space. Each burst is a testament to extreme physics, offering insight into gravity, magnetism, and the behavior of matter under conditions impossible to replicate on Earth. In the larger scheme, supermassive black holes serve as cosmic anchors, shaping the evolution of galaxies and contributing to the overall voice of the universe. The interplay between galaxies, dark matter, and black holes creates a rhythm, a subtle but detectable beat in the cosmos. Scientists interpret these patterns to understand cosmic history, from the distribution of galaxies to the expansion of space itself. Observations of galactic motion reveal that the universe is not static but dynamic, constantly shifting, colliding, and evolving. Each detected signal, each mapped interaction is a piece of a grand puzzle that tells a story far beyond human timescales. The cinematic aspect of observing galaxies cannot be overstated. Imagine a collision between two massive spiral galaxies, stars scattering, supernovae igniting, and central black holes roaring to life. The resulting waves of energy radiate outward, some eventually reaching our detectors as X-rays or radio emissions. These events are spectacular in scale and drama, yet they are distant and silent to the human eye. Instruments translate these cosmic performances into data we can comprehend, revealing a universe that is simultaneously violent, beautiful, and eloquent in its hidden language. Ultimately, galaxies are the building blocks of the universe's signal landscape. They produce, transmit, and sometimes obscure the signals we rely on to understand cosmic evolution. Each galaxy, with its myriad stars and unseen components, contributes to a broader chorus that defines the soundscape of space. Observing and decoding these signals allows humanity to trace the life cycle of matter, the flow of energy, and the evolution of cosmic structures, while reminding us that even the grandest of systems are subject to impermanence and change. The universe, in all its complexity, communicates through galaxies, and within their light and motion lies the story of creation, transformation, and eventual silence. Black holes are among the most enigmatic objects in the universe, regions where gravity becomes so intense that not even light can escape. They form when massive stars exhaust their nuclear fuel and collapse under their own weight, creating singularities surrounded by event horizons, boundaries beyond which nothing returns. Despite their invisibility, black holes communicate through the effects they have on surrounding matter. Gas and dust spiraling into a black hole form accretion disks that heat to millions of degrees, emitting powerful X-rays and gamma rays. Occasionally, relativistic jets are launched at nearly the speed of light, sending focused beams of energy across thousands of light years. These emissions make black holes not only observable but also essential participants in the cosmic conversation, shaping galaxies and influencing the distribution of matter. The most famous of these objects, supermassive black holes, reside at the centers of most galaxies, including our own Milky Way. Their immense gravity orchestrates the motion of stars and gas in galactic cores, controlling the formation and evolution of the surrounding environment. Some, like the one in the galaxy M87, launch jets so powerful they extend well beyond the galaxy itself, acting as cosmic lighthouses visible across the universe. Observing these jets provides insight into extreme physics, the behavior of matter under intense gravitational forces, the interaction of magnetic fields with plasma, and the limits of energy emission. In effect, black holes transform the void into a canvas of signals, each telling a story of creation, destruction, and energy redistribution. Intermediate mass and stellar mass black holes, though smaller, also contribute to the cosmic symphony. When two black holes merge, they produce gravitational waves, ripples in the fabric of spacetime that propagate across the universe. Detected first in 2015 by LIGO, these waves provide a new way of listening to the cosmos, revealing cataclysmic events invisible to traditional telescopes. Each detection is both a confirmation of Einstein's predictions and a revelation of the violent dynamics shaping the universe. The merger of black holes exemplifies the contrast between silence and sound. Despite being invisible and intangible in most senses, their interactions generate profound signals that can be measured and interpreted. Black holes also challenge our perception of time and causality. Near an event horizon, time dilates relative to distant observers, and space itself bends in extreme ways. Light and matter approaching the boundary appear stretched and slowed, creating optical illusions that reveal the complex interplay between gravity and relativity. The signals that emerge from matter just outside the event horizon, flaring X-rays or jets, offer glimpses into these extremes, allowing scientists to study physics in conditions unattainable on Earth. In this way, black holes act as natural laboratories, transmitting information across space and time even as they consume much of what falls within reach. The cinematic aspect of black holes is undeniable. Visualizations depict swirling disks of luminous gas, jets shooting across the void, and distortions of the surrounding space, creating an eerie, almost surreal spectacle. Observers, whether through telescopes or simulations, witness a dance of matter and energy at scales both incomprehensible and mesmerizing. Black holes remind us that the universe's loudest events often emerge from regions that are fundamentally silent, that true communication can come from places where conventional signals cease to exist. Yet black holes are also a source of existential tension. They represent the ultimate boundary, a point of no return, symbolizing the limits of knowledge and perception. While their emissions provide crucial information, the singularity itself remains hidden, inaccessible, and unknowable. In contemplating black holes, humanity confronts both awe and fear, awe at the cosmic power and elegance, fear at the profound silence and mystery lying beyond reach. They embody the delicate balance between signal and absence, between the known and the unknowable. Ultimately, black holes are central actors in the story of cosmic signals and silence. They consume, distort, and transform matter, yet simultaneously produce observable phenomena that inform our understanding of the universe. Each X-ray flare, each jet, each gravitational wave is a message encoded in extreme physics, a testament to the dynamic and sometimes violent nature of space. In their darkness lies both mystery and revelation, teaching humanity that even in regions where silence dominates, the universe has a voice waiting for us to listen. The cosmic microwave background is the faint afterglow of creation, a relic of the Big Bang that permeates the entire universe. First detected in 1965 by Arno Penzias and Robert Wilson, it revealed a universe filled with radiation left over from its hot, dense infancy nearly 13.8 billion years ago. This signal is uniform in all directions, yet contains subtle fluctuations, tiny ripples that encode the seeds of galaxies, clusters, and cosmic structure. To the naked eye, the universe appears calm and still, but the CMB is a whisper from the earliest moments of time, a persistent hum that reminds us of origins long before stars or planets existed. It is a cosmic record etched across space, waiting for attentive observers to decode its message. The CMB is more than a static relic. It is a dynamic storyteller. Variations in temperature and polarization reveal information about density fluctuations, dark matter, and the geometry of space itself. Scientists map these ripples with sensitive instruments, tracing the universe's evolution from a near-uniform plasma to the richly structured cosmos observed today. The data is both beautiful and profound. Swirls of color, subtle gradients, and anisotropies provide a visual representation of the forces that shaped everything from the largest galaxy clusters to the smallest stars. Observing the CMB is like reading a cosmic diary, where each entry contains secrets of creation, expansion, and transformation. Its discovery revolutionized cosmology. Before the CMB was detected, competing theories of the universe's origin vied for acceptance. Some posited a steady-state cosmos, eternal and unchanging. Others speculated on cyclical models. The uniform radiation of the CMB provided compelling evidence for the Big Bang, confirming that the universe began from an extremely hot and dense state. In this way, the faint hum across the sky became a decisive voice, cutting through uncertainty and reshaping human understanding of the cosmos. It demonstrated that even the quietest signals could carry profound truth, bridging imagination and empirical science. The cinematic imagery of the CMB is striking. Full sky maps reveal a mosaic of minute temperature fluctuations, patterns that appear almost painterly yet are precise records of early cosmic events. Observers can trace the emergence of structure, the interplay of gravity and matter, and the silent rhythm of expansion. Though invisible to the human eye without technological aid, the CMB is ever present, a constant background hum against which all cosmic events unfold. It represents both permanence and fragility, permanent because it is a relic of the universe's birth, fragile because its detection relies on sensitive instruments and careful interpretation. The CMB also emphasizes the theme of silence within the universe. While it is a pervasive signal, it is faint, almost imperceptible without amplification. Its very subtlety reminds humanity that much of the cosmos operates at the edge of detectability, with signals so weak or distant that without ingenuity they would remain forever unheard. It invites reflection on the limitations of perception and the importance of listening carefully, patiently, and with ever-improving tools. The universe's voice is not always loud. Often it whispers across time and space, rewarding those willing to attend. Beyond physics, the CMB has philosophical implications. It represents a connection to the earliest epoch of existence, a reminder of how far we are from the universe's beginnings and yet how intimately we are linked to its unfolding. Every photon detected has traveled across space for billions of years, carrying with it a message of creation, survival, and change. This hum of radiation is both a bridge and a mirror, linking the present to the past and reflecting the human quest to understand origins, purpose, and destiny on a cosmic scale. In studying the CMB, scientists and dreamers alike encounter wonder and humility. It is a signal that demands attention, interpretation, and respect. Its discovery transformed our understanding of the cosmos, proving that even faint, subtle noise can carry meaning of the highest magnitude. The cosmic microwave background is a persistent reminder that the universe speaks in many registers, that silence and sound are intertwined, and that listening carefully can reveal the deepest truths about existence. It is both a message and a challenge, to hear, to understand, and to appreciate the delicate, ongoing dialogue of the cosmos. Exoplanets have transformed our understanding of the cosmos, revealing that planets are not unique to our solar system but exist in staggering numbers across the galaxy. The first confirmed detection in the 1990s sparked a revolution, challenging centuries of assumption that Earth might be singular or rare. Today, thousands of exoplanets have been catalogued, varying from gas giants larger than Jupiter to rocky Earth-like worlds orbiting distant stars. Each discovery carries both scientific and philosophical weight. These planets are potential homes, laboratories of physics and chemistry, and clues in the search for life beyond our planet. Observing them is akin to opening windows onto alien worlds, glimpsing their atmospheres, compositions, and orbital dances across light years of space. The methods used to detect exoplanets are ingenious and precise. Transit photometry observes the slight dimming of a star's light as a planet passes in front of it, while radial velocity measures the subtle wobble of a star caused by gravitational tugs from orbiting planets. Direct imaging captures faint reflections of starlight off planetary surfaces, though only in select cases. Each technique transforms subtle variations in light and motion into a narrative about distant worlds, converting imperceptible signals into profound knowledge. The universe communicates through these minute changes, whispering the existence of planets otherwise invisible against the brilliance of their stars. Beyond mere detection, exoplanets offer insight into the potential for life. Scientists analyze atmospheres for chemical markers such as oxygen, methane, and water vapor, looking for patterns indicative of biological activity. These studies push technology to its limits, requiring instruments capable of detecting infinitesimal differences in light and spectrum. Each measurement is a dialogue across space, with the planet's faint signals conveying stories about temperature, composition, and potential habitability. It is a pursuit imbued with both hope and tension. Hope for discovery, tension in the uncertainty of interpretation. The diversity of exoplanets is staggering. Some orbit perilously close to their stars, scorched by relentless radiation, while others exist in cold, distant orbits, frozen yet stable. Some are tidally locked, showing the same face to their sun, creating extreme climates unlike anything on Earth. This diversity challenges preconceptions, reminding humanity that the cosmos is vast and creative, producing phenomena far beyond familiar patterns. Each exoplanet is a testament to nature's ingenuity, a participant in a silent symphony of orbits, gravities, and light interactions. Exoplanets also illuminate the interplay between silence and signal. Their presence is often imperceptible, detectable only through indirect effects on their host stars or subtle spectral fingerprints. Yet these faint traces carry profound information, demonstrating that even the quietest parts of the universe can communicate meaning. The act of detecting and interpreting these signals underscores human ingenuity and persistence, revealing how careful observation can transform near invisibility into comprehensive understanding. Philosophically, exoplanets challenge notions of uniqueness and centrality. The realization that planets abound, many within habitable zones, reframes humanity's perspective, suggesting that life might not be rare, that Earth is not necessarily special, and that the universe is more connected than once imagined. Each new world discovered is a reminder of possibility, a whisper from the cosmos hinting at the potential for companionship, for discovery, and for understanding our place in an expansive, dynamic universe. Ultimately, exoplanets are silent messengers, their presence encoded in light, motion, and spectral shifts. They extend the dialogue of the universe, providing clues about formation, evolution, and habitability across cosmic distances. Listening to these worlds is an act of translation, patience, and imagination, transforming faint signals into narratives of cosmic architecture, biological potential, and the boundless creativity of nature. In their detection and study, humanity learns not only about planets but also about perception, interpretation, and the profound interplay between silence and revelation in the universe. The search for extraterrestrial intelligence is one of humanity's most audacious quests, a deliberate effort to detect signals from civilizations beyond Earth. Unlike passive observation of stars and galaxies, this endeavor involves active listening, scanning the heavens for structured radio waves, laser pulses, or other anomalous emissions that might indicate intelligent origin. The challenge is immense. Signals are weak, rare, and potentially fleeting, traveling across incomprehensible distances while competing with the natural noise of the cosmos. Yet the implications of success are staggering, offering answers to profound questions about companionship, consciousness, and the uniqueness of life. Each detection attempt carries both hope and tension, a careful balance between expectation and uncertainty. The science of SETI, or the search for extraterrestrial intelligence, relies on sophisticated instruments like radio telescopes and optical arrays. Observatories such as the Allen Telescope Array constantly monitor the sky, analyzing terabytes of data for patterns that stand out from natural sources. Algorithms hunt for narrowband transmissions or repetitive pulses, signatures unlikely to arise from astrophysical phenomena alone. Each candidate signal is scrutinized extensively, distinguishing the human-made from the genuinely cosmic, the random from the deliberate. The process embodies both rigor and creativity, a scientific dance with the unknown. Philosophically, the search raises profound questions. What does it mean to be alone in the universe? If signals exist, how should humanity interpret them? Could we comprehend messages crafted by intelligences evolved under entirely different conditions, with senses and thought processes unlike our own? The silence so far is telling. It suggests either rarity, distance, deliberate quiet, or limitations in our listening techniques. Each null result is a reminder of cosmic scale and our perceptual constraints, but it also fuels curiosity, prompting refinement of methods and expansion of the search. Technologically, the search pushes boundaries. Scientists employ advanced signal processing, machine learning, and even quantum-enhanced detection methods to discern faint patterns. Observations must account for interference from Earth-based sources, cosmic background noise, and atmospheric distortions. The universe is not silent, but it speaks in a language we are only beginning to decode, requiring patience, ingenuity, and persistence. The cinematic tension of SETI is palpable. Imagine a distant star system, light-years away, harboring a civilization that has evolved technology and thought far beyond our comprehension. A carefully directed pulse crosses the void, arriving at Earth after centuries of travel. Instruments detect an anomaly, scientists debate its meaning, and the world waits with bated breath. Such moments, if they occur, blend wonder, fear, and anticipation, embodying the thrill and peril inherent in reaching across the cosmos. Even in the absence of confirmed contact, the search itself is a dramatic narrative, a human story of curiosity and courage. Yet silence dominates the story. Despite decades of listening, no confirmed extraterrestrial signal has been detected. This silence is ambiguous. It could indicate solitude, technological disparity, or intentional avoidance by distant intelligences. Each possibility carries emotional and philosophical weight, reflecting both the fragility and the ambition of human endeavor. The absence of evidence becomes a signal itself, shaping expectations, strategies, and interpretations in an ongoing dialogue between humanity and the cosmos. Ultimately, SETI exemplifies the interplay between hope and silence, action and inaction, listening and waiting. It transforms the vast quiet of space into a theater of possibility, where every observation holds potential significance. By striving to detect intelligence beyond Earth, humanity confronts its own curiosity, limitations, and desire for connection. The search is both a scientific enterprise and a reflection of the human spirit, determined, imaginative, and perpetually reaching for understanding across the silent, star-strewn void. The concept of cosmic silence extends beyond the search for life. It encompasses the gaps, voids, and absences that permeate space. Even in regions teeming with stars, there are vast stretches where no detectable signals reach us. These cosmic deserts, known as voids, are enormous volumes of space, often hundreds of millions of light-years across, containing few galaxies or other luminous objects. Their existence is both awe-inspiring and unsettling. They are proof of the universe's scale, the dynamic processes that shape matter, and the profound emptiness that dominates much of the cosmos. Standing metaphorically in the midst of such a void is to confront a silence that is absolute, a quietude so vast that human imagination struggles to comprehend it. Voids are not merely empty, they are active participants in cosmic evolution. The gravitational pull of surrounding galaxy clusters shapes them, stretching and amplifying their size over billions of years. Dark energy accelerates their expansion, pushing galaxies further apart and making the voids increasingly dominant in the large-scale structure of the universe. Within them, matter is sparse, interactions are rare, and light is faint. This creates natural regions of silence, areas where the universe's usual cacophony of signals is muted, leaving vast expanses almost entirely devoid of detectable phenomena. The contrast between bustling galaxy clusters and these empty voids heightens our perception of cosmic diversity and the extremes of existence. The cinematic imagery of voids is striking. Imagine looking across an expanse hundreds of millions of light-years wide, the faint glimmer of distant galaxies barely piercing the darkness. Gravity has sculpted the edges, creating filaments and walls where matter concentrates, leaving the interior emptier than anything on Earth could replicate. The silence is not literal soundlessness but the absence of significant electromagnetic signals, a stillness that dominates the scene. This emptiness challenges expectations. The universe is not uniformly populated, not a continuous ocean of stars, but a patchwork of activity and profound quietude. Voids also offer insight into fundamental physics. By studying their expansion and the motion of surrounding galaxies, scientists can measure properties of dark energy and test cosmological models. Their existence and behavior serve as natural laboratories, providing clues about the forces shaping the universe on the largest scales. Observing voids requires sensitivity to the faintest signals, yet their emptiness conveys information in its very silence. In this sense, absence becomes a form of communication. The lack of matter and light encodes the history and dynamics of the cosmos. Philosophically, voids evoke reflection on existence and perspective. Humanity often imagines space as filled with stars and planets, yet much of it is empty, reminding us of our smallness and the fleeting nature of detectable activity. The vast quietness of voids prompts questions about isolation, significance, and the thresholds of observation. They emphasize that the universe's voice is selective. Some regions are rich with signals, others dominated by silence, and understanding the contrast is essential to comprehending the cosmic narrative. Despite their emptiness, voids contribute to the universe's overall symphony. Their boundaries, interactions, and the way they influence surrounding structures generate subtle effects that ripple across space, detectable as gravitational distortions or shifts in galactic motion. Even in silence, they shape the dialogue of the cosmos, proving that absence is never truly void of meaning. Studying these regions expands our awareness of scale, complexity, and the interplay between activity and stillness. Ultimately, cosmic voids exemplify the tension between presence and absence. They are silent expanses, yet their influence resonates across the universe. By observing and understanding them, humanity gains insight into the forces that sculpt reality, the boundaries of perception, and the profound contrasts that define existence. Voids remind us that the universe's communication is multifaceted. It speaks not only through light, waves, and signals but also through silence, emptiness, and the spaces between, offering lessons in humility, awe, and attentive listening. Neutron stars are among the universe's most extreme and fascinating objects, remnants of massive stars that have undergone supernova explosions. Composed almost entirely of neutrons, they pack more mass than the Sun into a sphere barely 20 kilometers across, creating densities so high that a teaspoon of their matter would weigh billions of tons. These stellar remnants are laboratories of extreme physics, where gravity, magnetism, and quantum mechanics converge in ways unimaginable on Earth. Their presence is detectable through the signals they emit: rapid pulses of radiation, X-rays, gamma rays, and in some cases, gravitational waves. Each neutron star acts as a beacon in the cosmos, broadcasting its extreme existence across unimaginable distances. Pulsars, a type of neutron star, spin with incredible speed, some hundreds of times per second, emitting beams of radio waves that sweep across space like cosmic lighthouses. When these beams align with Earth, they produce remarkably precise pulses detectable by radio telescopes. This regularity allows scientists to study not only the stars themselves but also the interstellar medium through which the signals travel, revealing dispersion, scattering, and magnetic field structures along the way. The pulses transform neutron stars into both subjects and instruments simultaneously, revealing intrinsic properties and mediating information about the space they inhabit. Magnetars, another variant of neutron stars, possess magnetic fields trillions of times stronger than Earth's. These magnetic titans can release enormous bursts of energy, sometimes visible across vast portions of the galaxy. Starquakes and magnetic reconnections produce sudden flares of X-rays or gamma rays, ephemeral yet immensely powerful. Each burst is a dramatic punctuation in the quiet backdrop of space, a stark contrast to the surrounding stillness. Magnetars exemplify the universe's capacity for sudden, intense signals emerging from otherwise silent regions, highlighting the duality of quietude and revelation. Neutron stars also interact in pairs or groups, producing phenomena detectable through gravitational waves. When two neutron stars spiral together and merge, they create ripples in spacetime accompanied by bursts of electromagnetic radiation. These kilonovae events are both cataclysmic and illuminating, dispersing heavy elements like gold and platinum into the cosmos. Observing these mergers provides unparalleled insight into the physics of matter under extreme density, the production of elements essential for planetary formation, and the interplay between gravity and nuclear forces. In essence, neutron stars contribute not just signals but also the very building blocks of future worlds. The cinematic quality of neutron stars is remarkable. Imagine a tiny sphere spinning hundreds of times per second, emitting beams of energy with relentless precision, or a magnetar erupting with a sudden, brilliant flare against the backdrop of dark interstellar space. These events are both visually and conceptually striking, conveying the extreme conditions and dynamic forces at play. They underscore that even the smallest objects on a cosmic scale can have outsized influence, their signals rippling across vast distances and timescales. Philosophically, neutron stars challenge perception and understanding. They compress mass and energy into forms that defy ordinary intuition, forcing scientists and observers to grapple with scales, densities, and forces far beyond everyday experience. Listening to their pulses is an exercise in patience, precision, and awe, revealing that the universe's stories are often encoded in signals imperceptible without careful attention. The interplay between detectable emissions and otherwise silent surroundings embodies the contrast framing that defines cosmic observation. Ultimately, neutron stars are critical nodes in the universe's network of signals. Through pulses, flares, and mergers, they communicate information about fundamental physics, cosmic history, and the dynamic processes shaping matter. They exemplify how silence and sound coexist, quiet stretches punctuated by precise, powerful emissions that carry meaning across space and time. Observing and interpreting these stars deepens our understanding of the cosmos, reminding humanity that even in the universe's extremes, messages persist, waiting for those capable of listening with curiosity, ingenuity, and awe. Gravitational waves are ripples in the very fabric of spacetime, produced by some of the most violent and energetic events in the universe. First predicted by Einstein's theory of general relativity in 1916, these waves remained undetected for nearly a century until LIGO's groundbreaking observation in 2015 confirmed their existence. They are generated when massive objects accelerate, such as during the merger of black holes or neutron stars, sending distortions across space at the speed of light. Unlike electromagnetic signals, gravitational waves pass through matter virtually unimpeded, carrying pristine information about the events that created them. They are whispers of cosmic cataclysms, subtle yet profoundly informative, offering a new dimension in the way humanity listens to the universe. The detection of gravitational waves has opened an entirely new window on the cosmos. Instruments like LIGO and Virgo measure infinitesimal changes in distance, thousands of times smaller than a proton, between mirrors kilometers apart. These measurements capture the passing waves, revealing properties of the merging bodies, their masses, spins, and even the orientation of their collision. Each detection is a moment of triumph, translating near-invisible ripples into data rich with scientific meaning. Through these waves, we can observe phenomena that were previously undetectable, providing insights into the life and death of massive stars, the behavior of black holes, and the fundamental structure of spacetime itself. Gravitational waves also illustrate the contrast between silence and signal in the universe. Most cosmic events are invisible to human senses, yet some leave behind these subtle distortions that travel unhindered across billions of light years. They are the universe's quietest proclamations, detectable only by the most sensitive instruments. The waves carry no light, no sound, only the deformation of space itself, making them unique messengers of events that might otherwise remain entirely hidden. This duality, hidden yet revealing, highlights the layered nature of cosmic communication. The cinematic impact of gravitational waves is profound, even if they are invisible to the eye. Visualizations depict space itself rippling, a three-dimensional ocean of distortions emanating from merging black holes or neutron stars. These waves, though subtle, affect the distribution of matter and energy in surrounding regions, influencing cosmic evolution in ways that only now are becoming clear. Conceptually, they allow humanity to hear the universe, transforming abstract theory into tangible understanding and connecting us more intimately with distant cataclysmic events. Beyond physics, gravitational waves carry philosophical weight. They remind us that the universe is a dynamic, interconnected system where even regions appearing silent are active participants in cosmic narratives. Observing these waves challenges perception, requiring humans to interpret phenomena beyond ordinary senses, to listen through ingenuity and technology rather than direct observation. They exemplify the profound patience, persistence, and creativity required to translate subtle distortions into knowledge, bridging the gap between silence and understanding. The study of gravitational waves also redefines the concept of cosmic history. Each detected wave is a message from the past, arriving long after its source event occurred. Some originate billions of years ago, revealing collisions of objects that no longer exist, yet whose impact continues to traverse spacetime. In essence, gravitational waves are time capsules, carrying information about creation, destruction, and transformation across eons. They are both scientific treasure and poetic testament, signaling the ongoing interplay between the ephemeral and the eternal. Ultimately, gravitational waves expand humanity's capacity to perceive the universe. They demonstrate that even the subtlest distortions carry profound meaning, that the cosmos speaks in many registers, and that silence often masks deep underlying activity. Through careful observation and interpretation, we convert these whispers into understanding, revealing a universe both dynamic and delicate, where every ripple tells a story of creation, collision, and cosmic evolution. Listening to gravitational waves is an act of wonder, humility, and discovery, bridging imagination and science in the pursuit of truth across the silent expanse of space. The interstellar medium is the tenuous mixture of gas, dust, and cosmic rays that fills the space between stars, forming an intricate and dynamic web that shapes the galaxy. Though sparse by terrestrial standards, this medium plays a critical role in star formation, planetary evolution, and the propagation of signals across space. Within these clouds, atoms and molecules interact, creating regions dense enough to collapse under gravity and ignite nuclear fusion, birthing new stars. The medium is also a conductor and absorber of electromagnetic signals, altering their paths and polarizations, meaning that every pulse, flare, or transmission must navigate a complex environment before reaching observers. In this way, the interstellar medium is both a facilitator and a filter, silently influencing the universe's cosmic dialogue. Magnetic fields threading through the interstellar medium further complicate its character. These fields guide charged particles, shape the formation of filaments, and can even accelerate cosmic rays to near-light speeds. Turbulence and shock waves from supernovae propagate through the medium, compressing gas in some regions while dispersing it in others, creating an ever-changing landscape. The interplay between density, temperature, and magnetic influence produces subtle variations in signals, which astronomers must account for when interpreting observations. Every photon, radio wave, or cosmic ray passing through this medium carries imprints of these interactions, encoding information about the hidden structures and processes of the galaxy. Dust grains, though tiny, exert a disproportionate influence. They absorb and scatter starlight, reddening and dimming the light that reaches Earth while simultaneously re-emitting energy at longer wavelengths detectable in infrared and radio bands. Dust serves as both shield and messenger, hiding certain phenomena while revealing others. It catalyzes chemical reactions, fostering the creation of complex molecules that could seed prebiotic chemistry on nascent planets. In essence, the interstellar medium is an unseen but active participant in cosmic evolution, shaping the signals we detect and the environments that give rise to life. The cinematic perspective of the interstellar medium is mesmerizing. Vast nebulae glow in colors invisible to the naked eye, sculpted by radiation, magnetic forces, and gravity into filaments, bubbles, and cavities. Supernova remnants expand, sending shockwaves across the medium, while streams of gas spiral toward star-forming cores. These processes unfold on scales so immense that human comprehension struggles, yet through observations, simulations, and artistic visualization, the interstellar medium becomes a stage for cosmic drama, the birth, death, and transformation of matter writ large across space. The interstellar medium also illustrates the interplay between signal and silence. While its particles and fields transmit information, they simultaneously obscure and modify messages traveling through space. Observing pulsars, fast radio bursts, or distant galaxies requires accounting for dispersion, scattering, and absorption caused by this medium. In a sense, it acts as both communicator and gatekeeper, a filter that tests the patience, ingenuity, and perceptual skills of astronomers. Its complexity ensures that the universe's dialogue is never simple, requiring careful interpretation to distinguish intrinsic signals from medium-induced effects. Philosophically, the interstellar medium embodies the interconnectedness of cosmic systems. Every star, planet, or signal exists within and interacts with this diffuse fabric, highlighting the universe's continuity and interdependence. By studying it, humanity gains insight into the life cycle of matter, the propagation of energy, and the subtle forces shaping the galaxy. The medium teaches that even what seems empty is far from inert, that silence often carries hidden structure and influence, and that understanding the universe requires attention to both prominent events and the subtle background through which they propagate. Ultimately, the interstellar medium is a silent orchestrator, guiding the formation of stars, planets, and chemical complexity while mediating the signals that traverse the galaxy. Its presence is a reminder that the universe's voice is multifaceted. Loud bursts punctuate a pervasive, quiet medium that itself is active, shaping, filtering, and transmitting. By listening to and interpreting these interactions, humanity deciphers the hidden narratives of the cosmos, understanding that even in apparent emptiness, activity, information, and beauty abound. Dark energy is the mysterious force driving the accelerated expansion of the universe, an invisible presence that dominates over gravity on the largest scales. Though it cannot be seen directly, its effects are unmistakable. Galaxies recede from one another at ever-increasing speeds, stretching space itself and altering the cosmic landscape. First inferred from observations of distant supernovae in the late 1990s, dark energy remains one of the most profound enigmas in modern physics, representing roughly 68% of the total energy content of the cosmos. It is a silent, pervasive influence shaping the fate of the universe even as it eludes direct detection, compelling scientists to rethink fundamental notions of space, time, and energy. The influence of dark energy becomes apparent when comparing the motion of galaxies across cosmic time. Observations reveal that, contrary to prior expectations of a slowing expansion due to gravity, the universe is accelerating. Clusters of galaxies drift apart faster than predicted, voids grow ever emptier, and the cosmic microwave background provides subtle clues to the energy budget of space. Dark energy acts uniformly, a backdrop against which the drama of matter, radiation, and cosmic structures unfolds. Its presence underscores the contrast between the observable and the hidden, the detectable and the fundamentally mysterious. Cosmologists explore dark energy through multiple avenues, from precise measurements of supernovae to surveys of large-scale structure and gravitational lensing. These methods detect its influence indirectly, requiring careful statistical analysis and interpretation. Each observation is a step toward understanding the invisible scaffolding of reality, transforming silence into insight. The universe communicates its secrets not always through light or waves but through motion, geometry, and expansion, revealing the deep interplay between presence and absence. Philosophically, dark energy challenges perception and understanding. It embodies the tension between known and unknown, between observable phenomena and forces inferred only through their effects. Its dominance over the universe highlights the limits of human intuition, reminding us that the cosmos is governed by principles often counterintuitive to everyday experience. Observing dark energy encourages humility, imagination, and perseverance, emphasizing that much of reality's story is written in subtle effects, hidden in plain sight and accessible only through careful attention and reasoning. Cinematic depictions of dark energy often emphasize scale and abstraction, the stretching of space-time, galaxies receding into the distance, cosmic voids expanding, and the overall horizon of the observable universe extending ever outward. These visualizations underscore both beauty and unease, capturing the paradox of a force that is invisible yet dominates all motion, a quiet driver of cosmic destiny. The tension between motion and silence, visibility and invisibility, creates a profound narrative frame, evoking awe and curiosity about the ultimate fate of the universe. Dark energy also influences the ultimate trajectory of cosmic history. Its presence suggests a universe that may continue expanding indefinitely, growing colder and darker, with galaxies eventually slipping beyond observable reach. This projection imbues cosmic observation with urgency and poignancy, framing the current epoch as a fleeting window to witness the grand structure of existence. Dark energy transforms the universe into a narrative of both creation and inevitable isolation, a slow march toward a distant, silent future, emphasizing contrast between the energetic vibrancy of today and the quiet vastness to come. Ultimately, dark energy exemplifies the interplay between presence and absence, action and invisibility, signal and silence. It shapes the evolution of the cosmos, dictates the dynamics of galaxies, and frames the context for all other signals we observe. Though undetectable by conventional senses, it communicates through its effects, offering a narrative of cosmic expansion and eventual solitude. By studying dark energy, humanity listens to one of the universe's most profound voices, quiet, pervasive, and transformative, revealing that even what is unseen can dominate, direct, and define the course of cosmic history.